Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology in Hisar in Haryana. Today we will be discussing about the spectra of helium and alkaline metals under the paper Atomic, Molecular and Laser Spectroscopy. After completing this, we will be able to understand the spectra of helium atom, spectra of two valence electron systems basically, and the spectra of helium and alkaline metals in general, spectra of two electron system including their energy levels and the fine structure. Spectra of helium atom. The helium atom has electronic configuration of 1s2. These two electrons in the configuration are responsible for the valency of 2 and hence in deciding the general characteristics of the optical spectrum. The ground state helium has two 1s electrons. Both the electrons have L is equal to 0 and as N, L and Ml are same. Therefore, according to Pauli exclusion principle, their spins are antiparallel. Thus, for 1s2, S and L are 0 and hence J is equal to 0 and the ground state is 1s0. Now, assuming that one of the two electrons is excited to the 2p orbitals yielding a configuration 1s2 2p due to N is equal to 1 for the S electron and N is equal to 2 for the p electron. Pauli exclusion principle does not apply as the two electrons are non-equivalent. For the S and p electrons, L is equal to 0 and 1 respectively and thus L is equal to 1. The state is represented by the symbol P. The spins are either parallel or antiparallel, giving S is equal to 1 and 0 respectively. As the multiplicity is 2s plus 1, one gets triplet and singlet, and for S is equal to 0. The J values for the triplet are 2, 1, 0 and for singlet it is 1. The possible terms are therefore 2p, 2, 1, 0 and 1p, 1. In case one of the two electrons is promoted to various excited configuration, then the resulting states are singlet and triplet. The ground state configuration leads only to singlet, and according to Hund's rule, the triplet states lie lower than the corresponding singlet states. The table gives us the normal configuration, excited configuration, the value of N and the term corresponding to 1s2. There is no excited state configuration as we are considering it as a ground state, then the term is written as 1s0. And if the normal configuration is again 1s2 and the excited configuration is then 1s and s, and corresponding to this N is equal to 2, 3, 4 and term is 1s0 and 3s1. Similarly, for the excited configuration 1s and p, the term is 1p1, 3p210, and to the excited configuration 1s and d, the values of N are 3, 4, 5 and so on, and we get the term 1d2, 3d321. And for excited configuration 1s and f, taking the value of N as 4, 5, 6 etc., the terms comes out to be 1f3, 3f4, 3, 2. The figure corresponding to this table shows the singlets and triplets. The energy level diagram of helium is depicted in the figure. The energies of the ground state and the first few excited states of helium atom obtained from an analysis of the optical line spectra. The energy of the term increases in order of Ns, Np, Nd, Nf. For the same N, the lowest triplet is 2, 3s and the lowest singlet state is 1, 1s. The state 1, 3s is not allowed because of Pauli's exclusion principle. The energy difference between the 1, 1s and 2, 3s is quite large, that is 19.72 electron volt, reflecting the tight binding closed shell electrons. Helium atoms in singlet states having antiparallel spins constitutes parahelium, and those in triplet states parallel spins constitute orthohelium. The lowest state of orthohelium 2,3s doesn't combine with the ground state 1,1s. Those terms that cannot go to a lower state with the emission of radiation and correspondingly cannot be reached from a lower state by absorption are called metastable states. The 2,1s state is also metastable, as a selection rule delta L is equal to plus minus 1 does not allow any transition to 1,1s. The metastability of the 2,3s state is however stronger than that of 2,1s, as the transition 2,3s to 1,1s would contradict the prohibition of an ortho-para transition as well as delta L is equal to plus minus 1. However, 2,3s to 1,1s transitions can be caused by collision with other atoms or with the wall of a containing vessel that distorts the electronic structure of the atom and allow a change of spin to occur. The transition from one energy state to another is governed by the selection rule delta L is equal to plus minus 1, delta S is equal to 0, delta J is equal to 0 and plus minus 1. Allowed transitions between different energy levels gives rise to a large number of lines that can be put into two distinct systems of lines, a system of closely spaced triplets and a system of singlets. In the emission spectrum of helium atom, lines of singlet and triplet system may be grouped into 4 series each. That means principal series, sharp series, diffuse series, fundamental series. Principal series, 2 principal series for singlet are observed. One is from higher p state to normal 1,1s0 state, and member of this series lie in far ultraviolet region. This series also exists in absorption. Besides this, there exists another principal series whose spectral lines arise from transitions from higher 1p states to the 2,1s state. This principal series lie from infrared to near ultraviolet region. The members of the triplet principal series are due to transitions from higher 3p state to 2,3s state. The triplet principal series lie from infrared to ultraviolet region. In case of sharp series that arise due to transitions from S state to lowest p state, the lines of sharp series of singlet and triplet system lie in visible and ultraviolet region. The diffuse series arise from transition between higher D states to the lowest P state. The lines of this series for both singlet and triplet system lie in visible and ultraviolet region. And in case of fundamental series, this series arise from transitions between higher F states to the lowest D state. The lines of this series for singlet and triplet system lie in the infrared region. Under high resolution, the lines of perihelium system are single and those of orthohelium show closely spaced triplet structure, and this closely spaced structure is very difficult to resolve. The triplet fine structure is due to spin orbit interaction, and the figure shows 3p to 3s transition. The 3s state has one component, while 3p has 3 components. The one component of 3s state is 3s1, and the 3 components of 3p states are 3p2, 3p1 and 3p0. 3 lines are observed according to selection rules. Delta L is equal to plus minus 1, delta J is equal to 0, plus minus 1, and delta S is equal to 0 between these states. The adjacent figure shows the fine structure of triplet diffuse series. For triplet D, we have S is equal to 1, L is equal to 2, and hence the values of J is equal to 3, 2, 1. According to allowed selection rules, 6 transitions are possible. The complete spectrum should consist of 6 lines. Normally, the very close spacing is not resolved and only 3 lines are observed. For this reason, the spectrum is referred to as compound triplet. For helium, the component separations 3p0 minus 3p1 is 0.996 centimeter inverse, and 3p1 minus 3p2 is equal to 0.078 centimeter inverse. The terms of 2, 3p of helium are inverted, with 3p0 component lying highest in energy and 3p2 the lowest. Further, there is a breakdown of Lande interval rule, and this is due to spin-spin interaction. The figures represents a splitting of 3p210 to 3s1 transition and 3d321 to 3p210 transitions. The order is inverted in both p and d states for helium. Spectra of two valence electron systems. The electronic configuration of neutral atoms of group 2 elements, which are alkaline elements, are given as. The elements are beryllium, magnesium, calcium, zinc, strontium, cadmium, and mercury. The last two equivalent electrons in the group 2 elements are responsible for the general characteristics of the optical spectra. These elements in their ground state have two equivalent s electrons in the nth orbit, where n takes the values 2, 3, 4, 5 and 6, and therefore the ground state is n1 s0. On exciting one of these two electrons to higher spd of f orbit, one obtains a system of two equivalent electrons. These systems give singlet and triplet spd and f state as described in case of helium. The ground state configuration leads only to singlet states, whereas each excited configuration arising from the promotion, if an electron gives rise to singlet and triplet states with later lying lower than the corresponding singlet state, the figure depicts the energies of the ground states and first few excited states of strontium atom obtained from the analysis of the optical line spectra. This figure also shows some of the transitions allowed by selection rules. The fine structure splitting is not shown in order to avoid the complexity. Allowed transitions between different energy levels give rise to a large number of lines that can arise from transitions between closely spaced triplets and between a systems of singlet. In the spectra of alkaline earth metals, the lines of triplet system and of singlet system can be further classified into four chief series. The four series are principal series, sharp series, diffuse series, fundamental series. The principal series, which arise from transition from higher p states to the lowest s states, and sharp series arise from transition from higher s states to the lowest p state, while the diffuse series from transition from excited d states to the lowest p state, and the fundamental series comes from the transitions from excited f states to lowest d state. The regions in which the lines of these four series of singlet and triplet system lie for the strontium element are summarized in the table. Strontium singlet, the principal series lies in the visible and UV, and sharp series lies in the infrared and the visible. Same is with the diffuse series, and fundamental series, it lies in the visible region. And if we talk about strontium triplet, then the principal series is infrared and visible, and sharp series is visible and ultraviolet, and diffuse series is infrared and ultraviolet, while fundamental series is in visible and ultraviolet. Each series converge towards shorter wavelength to fit the wave number of the spectral line to hydrogen-like formula. The hydrogen-like formula means nu average is equal to Rz square 1 upon Ne double prime square minus 1 upon Ne prime square are successful only if non-integral quantum number are used. For each spectral series, the term T double prime is equal to Rz square upon Ne double prime square is constant and is wave number of series limit. Now, if we introduce the effective quantum number, that means Ne is equal to n minus mu, where n is an integer and mu is a fraction called quantum defect, that is 0 for non-penetrating orbits. As in case of alkali atoms, the penetration of various possible electron orbits into the atom core is measured by the deviation of the term values from those of hydrogen. Two methods are used to measure the penetration. First, by modifying the nuclear charge in the term value expression for hydrogen, and second, by modifying the principal quantum number. This leads to term values for the first as the term value for the first case where we modify the nuclear charge T is equal to R Z minus sigma square upon n square, and for the second case where we modify the principal quantum number, writing the term value T is equal to R Z naught square upon n minus mu whole square, sigma being the screening constant introduced already. Z naught is the effective nuclear charge when the electron is well outside the core. From this spectrum, ignoring fine structure, it is observed that triplet sharp and diffuse series have one common limit and singlet sharp and diffuse another. The frequency difference between common limit of triplet sharp and diffuse series and triplet principal series is equal to the frequency of the first number of the principal series, and this is referred to as Rydberg-Schusser's law. The frequency difference between the common limit of the triplet sharp and diffuse series and the triplet fundamental series is equal to frequency of the first member of the triplet diffuse series, which is called the Runge law. The same is true even if the fine structure is taken into account. So, first, second and third holds for singlet series also. Fine structure. The explanation of alkaline spectra reveals that lines of various triplet series have a structure known as fine structure. It is observed that all members of the principal series are composed of three lines with decreasing separation with increasing frequency and approach a single limit. All members of sharp series are composed of three lines with the same separation and approach a triple limit. All members of diffuse and fundamental series contain 6 lines, 3 strong and 3 satellites, and approach a triple limit. The fine structure in triplet series is due to splitting of various energy levels by spin orbit interaction as described previously in case of alkali atoms. In case of alkaline metals, in triplet travels we have S is equal to 1 and L can take values 0, 1, 2 and 3 for S, P, D and F states respectively. For S state, S is equal to 1, L is equal to 0 and therefore J is equal to 1. For 3S1, there is no splitting of the level. For P state, L is equal to S is equal to 1, therefore J is equal to 2, 1, 0 and P state is split into 3 components with different J values. Similarly, D and F states represented by 3D321 and 3F432 respectively splits into 3 components each. In the triplet principal series, transitions take place from 3P210 to lowest 3S1 level as shown in the figure and according to selection rules. Delta S is equal to 0, delta L is equal to plus minus 1, delta J is equal to 0 plus minus 1. 3 transitions take place. The spacing between the transitions depends on the splitting of P level with decreases with increasing N values as per the equation. Delta nu bar is equal to Ra alpha square Z raised to the power 4 upon N cube L into L plus 1. For large value of N, the splitting of the P level is negligible and as a result one observes a single transition in series limit. The figure shows the fine structure transition for sharp series that take place from different excited triplet S states to lowest triplet P state. The fine structure transitions for sharp series are depicted by the figure. As a result of allowed transitions, 3 lines are observed. The spacing between the lines of triplet is governed by the splitting of the lowest triplet P state. As the sharp series triplet separation is produced by the splitting of the lower 3P210 level on which all the transitions terminates, therefore it remains constant. Figure shows the fine structure transitions for the triplet diffuse series and take place from different excited 3D levels to lowest 3P level. Each of the 3P and 3D levels splits into 3 levels. As a result of allowed selection rules, 6 transitions are possible. The spacing between the transitions depend upon the splitting of 3P and 3D levels. For large value of N, the spacing between 3D 3 to 1 levels diminishes, and therefore 3D 3 to 1 levels are not resolved. As a result of this, only 3 transitions are observed whose spacing depends on the splitting of 3p210 levels. Some situation exists for the fundamental series. However, now for large value of n, the spacing between the transitions depends on the splitting of 3D 3 to 1 levels, which is constant. As for sharp and diffuse series, the transition terminate at lowest 3p level. Therefore, the large value of n, the spacing between transitions is same for both sharp and diffuse series. To understand these concepts, let us go for a few assignments. First is to calculate the Rydberg denominators for the first term value of the principal series of sodium. The wave number of transition is given to be 16973.7 centimeter inverse, and the value of R for sodium is 109734 centimeter inverse. So we need to first write down the spectral term T is equal to R upon Ne square, where we will be calculating Ne square as dividing the value of R with that of the wave number. So one gets the value 254. Coming to assignment number 2, the first ionization potential of sodium is 2/5 that of hydrogen. We need to calculate the effective nuclear charge of the sodium atom as far as the 3s electron is concerned. For hydrogen, you know Z is equal to 1 and N is equal to 1. Therefore, using the energy level formula, En is equal to minus Rz square upon N square, taking Z is equal to 1 and N is equal to 1, this becomes E1 is equal to minus R centimeter inverse, and we know the value of this as minus 13.6 electron volt. The ionization energy being 13.6 electron volt in case of hydrogen. Now we have been given the first ionization potential of sodium is 2/5 of that of the hydrogen. That means IH upon INA is equal to RZ square effective upon N square upon RZ square effective upon N square due to sodium. For sodium, N is considered as 3, and for hydrogen, Z effective is taken as 1. So putting the value of INA upon IH is equal to 2/5, we get the value of Z square effective as 1.897. The next assignment is the principal and sharp series for the lithium atom converge to continua at two different values given as 43487 and 28583 centimeter inverse respectively. Calculate the quantum defect for the common term in each of these series, where R lithium has to be given 109729 centimeter inverse. The common term for sharp and principal series is 2p term. The wave number position of this term is given to be 28535 centimeter inverse, and we know that T is equal to R upon Ne square. Therefore, Re square is equal to R upon T. We have the value for R, we have the value for T. Dividing, we get the value of Ne square as 3.83896, and taking the under root, we take 1.9593 as value of Ne. So making the difference of N and Ne, we get the value of M as 0.0407. So summarizing what we have learned in this module is, a 2 electron atom or helium like ion is a quantum mechanical system consisting of one nucleus with a charge of Ze and 2 electrons. This is the first case of many electron systems where the Pauli exclusion principle plays a central role, and it is considered as a 3-body problem. The important 2 electron atoms are hydrogen anion Z is equal to 1 and helium atom Z is equal to 1, lithium ion Z is equal to 1, beryllium ion Z is equal to 1, boron ion again Z is equal to 1. The optical spectrum of the 2 electron atom has 2 systems of lines, a para system of single lines and an ortho system of triplets, closely spaced group of 3 lines. The energy levels in the atom for the single lines are indicated by 1s0, 1p1, 1d2 and 1f3, and for the triplets some energy levels are splitted 3s1, 3p2, 3p1, 3p0, 3d3, 3d2, 3d1, 3f4, 3f3, 3f2. Alkaline earths and mercury also have spectra with similar features due to the two outer valence electrons. Thank you.